The free body diagram as the first thing in mechanics course. You have distinguished the internal force, external force, okay? And after learning the strength of material, you know the stress, okay? But for applied mechanics of undergraduate, you just know rich body, okay? But actually, this is the internal force and equilibrium, the free body diagram. Yeah. All right, and the stress here is equal to E epsilon equal to E Z curvature is equal to E Z M over EI is curvature, and E divided by M Z over I is the stress function of the any point at Z coordinate, and with the bending moment that cross section, and with the I value, you can get the stress value at any Z point. So this will be the Z sigma x from equal to M plus dm over Z over I. Okay? So that's the difference between that is that corresponds to dm. So on AB face, my actual force is equal to the integration of sigma x times dA. AB from sigma x, this sigma x times dA, and from dA is equal to okay, let me see. It's equal to mx z over I dA. Okay, and actually the dA is from z1 to half h. z1 to half h. Okay, this is my from z equal to half h to z1. Okay, or from z1 to half h. Okay, half h. And the nx prim on CD, the nx prim, the actual force, equal to from z1 to half h, and will be sigma at x plus dx times dA, and that will be z1 to half h mx plus dm over I times z times dA. Okay. Actually, the dA is equal to what? B dz. Okay. B dz. The width is B. Okay. This is dA equal to B dz. This B. Okay, B dz. I just integrate the force from bottom to here. Okay. Now we also have a force on the AC face. Okay. So let's direct to the equilibrium. Or forces in x direction. That will be tau at z1 times the b the width, times dx, this area, ddx, equal to nx prime minus nx. That will be equal to from z1 to half h dm z I b dz, the dA. Okay. Anyway, okay. So actually the b can be cancel each other, and dx can take here. So I have a tau at z1 equal to z1 to half h dm dx z over I dz. Okay. So this can be further, and you know dVm is equal to V shear. So the shear and the I can be taken out. That will be V over I integration from z1 to half h and z dz. All right, and the result will equal to V over 2I half h square minus z1 square. So that's a shear distribution inside quotation with respect to the z coordinate, z1 coordinate. Okay, so let me draw the diagram. And actually, this is and this here, because this is very small, but this is for also dx, and this so for here, this is z1. So at here, we have a shear stress tau at z1, same as this. So the cross section will have a shear stress in vertical. Okay, for the element here. The shear stress is horizontal, but it's equal also vertical. The shear stress. Okay. Yeah. So this is all right. Yeah. Okay. This is my x, and this is my z. The shear distribution like this. Okay, the value like this, and this is for the stress at z1. Any value is equal to Vx divided by 2I half h square minus z square. Okay, you can take out the z1. So just like this. And you can see for z equal to 0, this will maximum. So this value will have 8I Vh square. Okay, this maximum value, shear stress. At z equal to half h, 0, minus half h, 0. So like this parabolic. So this is a shear stress distribution in the cross section tau xz. Okay, tau xe. So this is a cross section at x, and here I have a total shear V x. And the detailed stress, the total, this is resultant force at that cross section. It's from the equilibrium, from the bending moment of things. Okay? So after you got this, you can plug into this equation, you can get a shear stress at any point inside the beam. Okay? So this is the beam theory you can get. All right. So that's beam theory, and this beam theory have some because it's assumption, and it will have some limitation on this theory. Okay. So for a beam, this is a beam. This is a beam, the length L, and this is the thickness of H. Okay, and we have an arrow. Okay, arrow as a function of LH ratio. Okay. And this the value something like this. So for the acceptance arrow, okay, because this is acceptable, so this value is